Yeah, first of all, I'd like to say thank you very much to Boumediene and to the conference organizers for having me. It's been just an amazing experience these past few days. So I'm going to talk about something which actually harkens back to some of the talks from yesterday evening on learning dynamical systems, and particularly interpretable models from dynamical systems from time series data. And I'm really going to focus on the case where we don't have full observations of our dynamical system state, but actually only see some partial observables of some of its coordinates. So as a motivating example, there we go. Imagine that we have some sort of a video of a neuron. It's been optogenetically modified. So all that we actually get to see from it, this pointer works. Oh, there we go. Do I click this button? Yeah, I'll use the mouse. So all that we see from it is essentially just this video, and from this video, whenever the neuron fires, the light field increases in the body of the neuron, and from this we just record the average light field, which is this orange curve, right? So this is very typical of a lot of like biological data. We get some sort of average recording, one single scalar observable. Clearly, a neuron is most likely not a one-dimensional object. So the question is, can we learn a simple dynamical system model that can reproduce this observable dynamics and teach us something about the dynamical processes in this system. So before I dive in to talk about how we do this, I want to say that this was a project that I worked on throughout my PhD under supervision of Jorn Dunkel in the MIT Math department in collaboration with the students Alistair Hastewell, Dominic Skinner, who are now at Northwestern, and Jan Totes, who was at MIT as a postdoc at the time. So of course, I'm kind of preaching to the crowd when I say that learning dynamical systems is a very large area with plenty of applications nowadays. And there's been so much progress on this. So there's been a lot of focus on interpretable methods, learning dynamical systems in some sort of a basis or through some sort of interpretable right-hand sides that have some sort of physical meaning. We saw a great talk by Professor Horesh yesterday on this. And also, there's been a lot of work on compressed sensing for learning ODEs from Professor Lai's group and also from the Kutz group. There's been plenty of interesting work also from many people in this audience on kernel methods and Gaussian processes for learning right-hand sides of dynamical systems from data. And of course, we had a whole section yesterday on reservoir computing for predicting dynamical processes. The general kind of formulation is you're given some sort of time series data, x of t, and you try to learn this type of an ODE, x dot equals f of x. And the real question that I want to address today is what happens if you're given very limited observations of your dynamical system. So what if, for example, you have an n-dimensional dynamical system, but you only observe like the first coordinate, x1? Can you come up with a way to learn a model that can essentially match or predict the dynamics of this coordinate? And what does that tell you about your original dynamical system that you recorded? So there's kind of two contrasting approaches. There are two ways to really think about this problem. One is to try to write down a model for x1 just in terms of itself and its higher order derivatives, or in the discrete time case, time lags. So I'm going to give a quick review of why this is even possible to do. So this actually started with investigations in the 90s where people were interested in ways to rewrite three-variable chaotic systems in a higher order form. So there was essentially this question posted by Gottlieb in the American Journal of Physics, where he took a chaotic three-variable model from one of Sprott's earlier papers and noticed that through some simple algebraic manipulations, you could arrive at a third-order model just in X, which if you have good eyesight, you can see it actually has a rational form on the right-hand side. Then Linz, around the same time, actually wrote out that for the Lorentz system, you can write out a third-order model just in X. So it's very nice that this classical example also had this type of a jerky form in one of its coordinates. And there were papers actually generalizing this and showing that there are whole classes of chaotic systems that whose coordinates can be written in this jerk form. So really the focus was on third-order models, but this type of algebraic substitutions to reduce a multivariate model to a higher-order model of one coordinate can be done for more than three coordinates. Okay, but there are some downsides to this, which are that very often these models, these higher-order models, will contain rational terms. So this can make them hard to integrate. Of course, they become implicit ODEs. And also, many times these models are not going to be sparse. They can contain many irrational terms on the right-hand side, which makes them hard to learn in practice. So the approach that I'm really going to focus on today is trying to learn a different class of models, which are going to be of first order, but they're going to be multivariate. So in particular, we're going to try to predict the dynamics of x1 by making x1 the first coordinate of a multivariate model, where the rest of the coordinates h2 through hn have no data, they're unobserved, but we hope that we can learn them to help drive the dynamics of x1 to fit our observed scalar data. So as a particular example, imagine that we're interested in this type of a polynomial dynamical systems class. So really, all this dynamical system is trying to do, it's trying to fit all of its parameters, which here are the coefficients in front of the polynomial terms on the right-hand side, the timescales, which allow some variables to evolve faster than others, and the initial conditions of all of these variables. And it's trying to fit them in such a way such that the first coordinate x1 of our model matches the observed data that we've received. So as a general kind of... So I'm really only going to show it for 2 and 3 variables because for like many oscillatory and chaotic systems, you can get away with that few. But in practice, it would be best to search over a range of n's to find essentially some balance between model error and parsimony. Yeah, but I'm really going to stick to 2 and 3. Okay, so the general kind of structure of this talk that every example is going to follow is we're going to be given some amount of time series data, usually a couple of oscillations or periods of some sort of dynamics, possibly corrupted by a good amount of noise. Then we're going to tune all of the parameters of this model through an optimization procedure such that the first coordinate of our model matches this observed data. And then lastly, we're going to check that outside of the training window where we gave our optimization data, the model continues to do what we expect. So either it continues to oscillate if we have a periodic dynamics, or it continues to predict the dynamics for at least a couple of Lyapunov exponents if we have a chaotic system. Okay, so really kind of the main thing I should mention is how do we actually tune all of the parameters in this dynamical system model. So first what we can do is we can write out a cost function. So here all it's saying is we want the first coordinate of our dynamical system model x1 to match the observed scalar data that we've seen. And also I've added some regularization terms here to make the right-hand side as sparse as possible. So as many of the polynomial coefficients go to 0. Okay, and then the name of the game is we want to plug this into our favorite gradient optimizer in PyTorch or Julia or any library you want and run a gradient method, which means we need to actually take the gradient of the loss with respect to all of the parameters of our model, which I repeat are the initial conditions, the coefficients, and the timescales. So how do we actually do this? So we can just write the chain rule out for grad L of P. And we see that we get this complicated term highlighted in red, which is the gradient of the simulation of the first coordinate of our model, x1, with respect to all of the parameters p. So to actually compute this thing, we use something known as the forward sensitivity method. And the way it works is you essentially take your original model system, which I've rewritten here on the bottom left, and you take the gradient of each equation with respect to p, which gives you essentially an NP system of sensitivities or gradients. And now you take your original system, you append on your system of gradients, and you simulate all of this forward in time. And from this, you extract a gradient of x1 with respect to p, which you plug back in to your expression for the gradient of L. So this is just a summary of what a forward sensitivity method is. I'm assuming some of you might be familiar with this. And there's also something known as the adjoint sensitivity method, which is very closely related to the kinds of backpropagation algorithms you use in training neural networks. So, and just to mention, there's several really good libraries now to do this. One is the Julia SciML ecosystem, which is the one that we use in our code. Also, Jan Dragono showed yesterday this great Neuromancer library in Python, which is also capable of doing these types of backpropagations. Okay, so now we actually have a way of tuning the parameters of our model, and I want to show how this works on a simple example of a prototypical neuron model known as the Fitz-Unoguma oscillator. So this is a 2-variable polynomial model. The first variable v describes the voltage of a neuron, and the second variable w describes essentially the calcium concentration. We're going to assume that only the voltage is what we can measure. So we'll simulate this forwards in time for a couple of periods, and we're only going to be given access to observations of the voltage corrupted with some 30% random Gaussian noise. So now I want to show how we actually use gradient methods to fit a cubic polynomial model to this partial observable of the first coordinate of Fitz-Nagumo. So what we can do is we can take a cubic polynomial model in two variables. So here, if you look at this bar plot, we've included every possible polynomial term up to cubic in the two coordinates. And we're going to train all the coefficients of this model through gradient optimization, such that the first coordinate matches the observed voltage recordings that we've been given. And we see that after this training, we actually get a relatively nice fit to the voltage recordings, and we have a dense polynomial model that fits this. So of course, we don't want all these terms on our right-hand side, so we use a very classical technique of sparse thresholding, which is the same thing that's used in the Cindy algorithm. We cut out those terms which are small, and we re-optimize. And again, we get a reasonable fit to the data, and now a sparser-looking polynomial model. So we repeat this iteration until we arrive at a very sparse-looking polynomial model that gives us a nice fit. Okay, and just to mention, we couldn't use something like Cindy to do this because we don't have access to the second coordinate W, so we can't actually turn this into a regression problem. We really have to use gradient methods to do this optimization. Okay, so now we've arrived at a sparse polynomial model. Let's see if it compares with the true Fitz-Nagumo equations. So this is the true Fitz-Nagumo system on the right, and this is a system that we've learned. And of course, they don't correspond to each other, which is really not surprising, right? We see we have a v-cube term here in the w dot equation, whereas in true Fitz-Nagumo, it's not there. But this really makes a lot of sense because we were never given this w coordinate as an observable, and therefore what we've really done is we've learned a diffeomorphic transformation of the true w coordinate of Fitz-Nagumo. So how do we actually test this? One way to do it is take the v dot equation in the true Fitz-Nagumo system, solve for w as a function of v and v dot, and plug it into the w dot equation. So this gives us a second order equation just in the voltage. And we can do the exact same thing for our learned system. And given the fact that we trained on 30% Gaussian noise data, we actually get relatively good agreement in the coefficients of this second order model. So this kind of completes the circle that we were using this form of multivariate first order polynomial differential equations because it's very nice to run gradient optimization on them. But when we actually want to do model comparison, we can use these types of higher order reduction techniques to check whether the model that we've learned compares with the ground truth or not. Okay, and indeed, like I said, you can actually test that you can start with Fitz-Nagumo and find a way to diffeomorphically or linearly transform the W coordinate such that we get back the sparsity pattern for the model that we learned. So they are indeed diffeomorphically related to each other. Okay. More generally, there's also an interesting mathematical question of what class of diffeomorphisms take polynomial differential equations to other polynomial differential equations. And it turns out that there is a pretty large class that you can write out, which takes this type of functional form. It takes the observed coordinates x to themselves, and it takes the hidden coordinates through this type of a linear mapping plus a polynomial transformation of the observed coordinates. So you can check that any such diffeomorphism will get you to another polynomial dynamical system. But of course, not all diffeomorphisms will be of this form. There's actually a much larger class of diffeomorphisms that take polynomial ODEs to polynomial ODEs. This is just one of the classes. Okay. So to summarize, really, what has this experience taught us? It told us that polynomial dynamical systems, if you only observe a subset of their coordinates, there exist many ways to diffeomorphically transform their unobserved coordinates to get back to an equivalent model that will give you the same exact dynamics in those coordinates that you did observe. So just to list out what some of these diffeomorphisms or symmetries might look like, imagine that you have a differential equation system with one coordinate that's observed and three that are unobserved. Then you could take those unobserved coordinates and translate and scale them. You could permute their order, or you could find other nonlinear transformations of the hidden variables, and this would all give you back other types of polynomial dynamical systems that give you the exact same simulations. Okay, so this was really one of the realizations. Another thing that we learned is that sparse iterative thresholding, like I showed on the previous slide, causes some issues. So very often when you remove terms one at a time, you can get stuck in models that no longer give a good fit to the data. So essentially, this type of backward selection procedure can get you stuck in bad minima. You can reach a sparse model that is able to fit data very well, but then if you clear its coefficients, set them to 0, and try to re-optimize it, it will no longer fit the data through gradient descent, which is kind of surprising. And perhaps more importantly, we realized that because there's this whole class of equivalent models that can produce the same dynamics in the observed coordinates, we really need to run optimizations many times and compare all of the possible good parsimonious models that can fit our data. So this kind of goes back to something that Professor Haresh was talking about in his talk, that we really need to search over many different types of models and try to balance model parsimony with model fit. Okay, so this kind of leads into the algorithm that we developed for actually fitting dynamical systems from partial observations. I'm going to show this again on the example of Fitch-Nagumo to begin. So the way that it works is, imagine that you're given, again, just the voltage of this Fitch-Nagumo neuron, but not its calcium concentration. Then what you can do is you can take some polynomial class of 2 variable models and generate a bunch of them with random coefficients and optimize all of them through gradient descent, like I showed before. After you do this, you obtain a whole bag of models, and you can cluster them based on their coefficient values. So from this, you can look at the largest model cluster, where essentially the largest model cluster is essentially the most popular type of model that's been chosen, and you can analyze it. So this is essentially what I'm going to do. You throw out all the models that don't fit, and you look at the largest model cluster that remains, that fits your data well. So if I do this with Fitch-Nagumo, where again, I've optimized a bunch of models of this polynomial form with up to cubic nonlinearities. If I plot the largest cluster in this heat map, we actually see that some of the polynomial terms have coefficients that are very well concentrated around their mean, whereas some are quite spread out. So for example, you can see that the 1v and h term in the v dot equation are very nicely concentrated and far from 0. So really, this kind of implies to us that we can rank these model terms based on essentially how concentrated they are. So we can use this metric, which is the coefficient of variation, which is just the standard deviation divided by the mean. And if we rank based on this type of a statistic, we actually see that the top 7 terms in our ranking exactly give us back the terms that appear in the Fitch-Nagumo equation. So this now gives us a way to balance model complexity with model error. And we can do this from more than one observable. So for example, here we have the chaotic Lorentz attractor, which is 3 coordinates. If we only observe x and y, but not z, we can again use this type of model ranking procedure, and we're able to exactly find that the data comes from this type of a polynomial dynamical system, which is Lorentz. Okay, it turns out in the literature on partial observations, learning the Lorentz attractor from just the x coordinate is a much harder problem. It usually takes much more compute power and model searches to nail down the form, and oftentimes algorithms actually don't find the correct form. So we tried it on our example, and we found a very predictive model which even agrees with the attractor of Lorentz in derivative embedding space, only giving it this x coordinate. But we found that our model form is actually not exactly correct because it's missing a linear term in the y dot equation. So we wanted to investigate kind of why this is happening, where, like why is our model so predictive if it's missed a linear term? And we can again test this through model reductions like I showed with the Fitch-Nagumo example. So we can start with the true system of the Lorentz equation, and we can again solve for y and z to eliminate them and end up with a higher order equation just in x dot, x double dot, and x triple dot. So this is a 3rd order equation that the x coordinate of Lorentz satisfies, just like in the original Linz paper. And we can do the exact same thing with the model that we've learned. So here we have a 3 variable model. We again eliminate y and z through these kind of painful algebraic manipulations, and we end up with another higher order model. Okay, so now we're in a position to actually compare these side by side. And we see that all the terms that appear in the true reduced Lorentz model also appear in ours. So we can actually match the coefficients, which gives us this system of equations. So essentially, now this is quite nice because we can ask the question, is there a way to set the coefficients of our model, P1 through P7, to satisfy this system of equations. And it turns out there isn't. This is an inconsistent system, so this already proves for us that the model that we've learned in no way can be equivalent to Lorentz. However, there is a way to set P1 through P7 such that all but the first equation are satisfied. And if we plot the coefficients that our model actually learned when we optimized it through a model search, we find that this is exactly what it ended up doing. It ended up satisfying all of these equations except for the first one. So it's really telling us that our model search optimization procedure has tried as best as possible to match Lorentz, even though it was off by one of the terms, which was quite nice. Okay, now I want to show two experimental examples, and this is essentially where I'm going to end, so we might have more time for questions. So the first example that I want to show, we pulled some data of actual voltage recordings from squid axons. So I drew the squid. It took me a little bit of time. So essentially, we took 3 such squid axon recordings, and we tried to fit a cubic polynomial model where the first coordinate of this model would try to match the voltages in all of these 3 cases. And we ended up finding that indeed there was one cubic polynomial model that could do this, and its coefficients varied quite smoothly over these 3 examples, and it had a nice stable limit cycle. The last example I want to show here is a chemical reaction known as the Belousov-Zhabotinsky reaction. It has something like 20 or 30 chemical substrates which all interact with each other, and they change the color of the solution from red to blue in this oscillatory way. So what we did is we essentially processed these videos of the chemical solutions that Jan Totes created in our lab, and we put them on this color scale where essentially red corresponded to a small value and blue corresponded to a high value. So we were able to extract these color oscillations. And we ran 3 such experiments, extracted these videos, and tried to fit one polynomial model to all of these examples. And we found that indeed there was a way to do this. It essentially was a model of a linear quartic form, which was something that was inspired by some of the theory on 2-variable Belousov-Zhabotinsky models. And again, the coefficients for all these models varied quite smoothly over these examples. And here I've plotted one of the phase plane diagrams for this model, and we see that it has a stable limit cycle, and also the null-Klein shapes for both coordinates are very close to what you actually get from theoretical BZ models in the literature, which was kind of a nice proof that we were getting a reasonable chemical model back out. Okay, so in summary, that's kind of where I want to end for today. I showed that you can use these sensitivity gradient methods to optimize polynomial or generally nonlinear models and fit them to partial observations, something that you wouldn't be able to do with a regression approach. And furthermore, actually, even though you can't use higher order models so easily for optimization, they're actually a very nice tool for validating whether your inference framework works on ground truth examples. I'm happy to take questions.